Welcome everyone to this session on chemical science and engineering from daily life to space technology. Science is exciting and ever inspiring. We all know life forms evolved from single cells to gigantic blue whales and dinosaurs on one hand and intelligent Homo sapiens on the other. And these humans have evolved from cave age to space age. And science formed the vehicle for this aspiration-driven progress of humans. We may study science in separate disciplines. However, they all contribute to mankind equally and significantly, and almost always they work together. Science in general and chemical science in particular enabled us in understanding nature and its ways, utilizing the natural resources in the most effective way, producing numerous new materials to lead a modern life, securing food and water, saving us from diseases and ensuring health, and so on, and ultimately utilizing space for betterment of mankind and exploring the universe. Here, we will have a glimpse of the role of chemical science and engineering, of course, from daily life to space technology in every walk of human's life. Let us consider one common example, the morning toothpaste. This is a classic example of designing a chemical system for various functions. It has calcium carbonate, which acts as an abrasive, glycerin, which makes toothpaste foam in the mouth, sodium lauryl sulfate, which acts as a detergent used to loosen plaque, and so many of them, titanium dioxide, which gives a whitening. And many such chemicals are designed and it constitutes the toothpaste. And another one you consider what we use in daily life, which is soap, which is the cleaner and of course the savior of us today. We all know that without soap you cannot think of removing grease and oil. How it is coming? Well, water cannot have affinity to grease because of the inherent molecular structure. Now, how to take into account this? A specific little large molecule is designed which has got one side water loving, other side water repelling. Now, when you mix this soap with water, you get an emulsion. This emulsion, now, when in contact with grease, the hydrophobic part, the water repelling part can approach grease and then water can easily remove that. A very beautiful and simple way of science has found its application for common need. Now let us understand rice, our staple food. Well, rice has got starch up to about 80%, water 12% and protein 7%. Now let us see how it transforms before it reaches us. There is a chaff, which is the overall cover. It gets removed, then you find bran, and then bran residue, and then geril germ, and finally endosperm. What is this endosperm is about? It consists of amylose and amylopectin, and this is mostly what we all get for eating. Now, this granule, rice granule, is crystalline in nature, and this crystalline starch is non-digestible to humans. But we have found a way to secure our food by cooking the starch. Now, when you cook the starch, the semi-crystalline starch material, it breaks down and amylose comes out of the granules. And the beauty element is an enzyme that is present in human's mouth, the amylase, breaks it down into digestible, smaller sugar molecules, maltose. And maltose is sweet. And the other important thing is, human saliva contains amylase, and this salivary amylase of humans is 6 to 8 times that of chimpanzees. A major evolutionary change is very visible over here. Now let us see color and flavor of foods. We are all fond of color and flavor of foods. Let it be toasted bread, let it be browning of meat, fried onions, roasted coffee, maple syrup, biscuits. Anything you take, it has got an attractive taste and color. How it comes? We don't need to add anything. It's a very simple reaction. The carbonyl groups of sugar reacts with the amino group of amino acid proteins. In presence of heat, it produces molecules of varying structure and flavor. And this so-called Maillard reaction is the reason for mouth-watering cracker-type flavor of baked items. Now let us move on to nature's big factory. What this big factory is doing, it just processes the simplest of molecules we can think of. Carbon dioxide and water reacts in presence of light to form hydrates of carbon. We call it photosynthesis. And this reaction is the source of food and energy for all the living being on earth. And it does a great thing for the earth. It fixes the carbon in the atmosphere in the form of food, in the form of structure of living beings, and in the form of energy for all. And of course, it has turned out to be the fossil fuels that humans have very beautifully used for his progress. Now, this brings us to a very important point. It comes us to carbon cycle and energy cycle. Let us see how it happened over the years. Around thousands of years ago, through photosynthesis, carbon dioxide was getting converted to varying materials, and it also formed a part of all living beings. And when we used energy, it went back as carbon dioxide, and this cycle was going in a sustainable fashion. But when humans started using this for energy needs, when humans started the fossil fuels as energy needs, we started seeing a one-sided cycle in which the carbon dioxide started liberating and going into atmosphere, which is not coming back as it is expected. What is the result? The natural carbon cycle is getting disrupted. The result is the exponential rise in carbon dioxide in the atmosphere. It has touched about 35% increase within the last 200 years. What is the result? It has resulted in almost a degree rise in the average global temperature. Here we may look at, in a chemical science point of view, if you see, humans have used fuels for his progress. He depended on firewood, then coal, then petrol, diesel, and then LPG, and so on. Firewood consists of a very complex molecular structure. You can see it over here. Now, when it moved on to coal, it becomes a little more structured. And then when it moved to petrol, diesel, a little more simpler and linear molecules, we started using it. And then LPG, a very simple molecule. The result is we are moving from a complex molecule, a very simple molecule. And another point is, this has resulted in increase in hydrogen to carbon ratio. And this has a very important factor. For per capita energy requirement, you don't release that much of carbon into atmosphere. Now, this brings us to the fuel of future. It is a natural transition. How we can find the fuel of future? You know, the simplest of the reaction. Water splits into hydrogen and oxygen. It is a very well-known water electrolysis. And of course, hydrogen is a good fuel. Why don't we think about the reverse reaction? Oxygen from air is combining with the hydrogen that you have obtained from water. It goes back to water. Now, you will also get energy back, because energy is what you have pumped in to split them, so you should get it back. Now, the point lies in getting this energy in the form of electricity itself. That gives us very high efficiency. Now, the conventional process says hydrogen and oxygen, when it combines, it forms water and heat. But now, if you devise a system such that these will combine and form electric energy directly, your efficiency goes from 30 to 80%. There lies the beauty of the technology. Now, this technology is what we call as fuel cells, where hydrogen is separately reacting to form H+ ions and oxygen reacts with H+ ions, forming water, thereby producing electrical energy. And now this brings us to a dream energy cycle. A cycle we lost long back, what we referred little back, and now we are getting back to this. How it is? Here, water goes to hydrogen and oxygen. When you consume energy, it goes back as water. The same way nature sustained an energy cycle with carbon, now we are able to have a hydrogen-based or water-based sustainable energy cycle for all our industrial and transportation needs. So this is a technological marvel. Now, this is a technology that has already been used in space missions. Of course, space missions have used this kind of new technologies, and thus it has pushed the frontier of science and technology. Let us discuss about the space missions. Space missions are in various domains. We have launch vehicles, we have satellites, we have reusable launch vehicles, we have manned missions, landers and rovers, interplanetary missions, and so on. When it comes to space mission, you have extreme space environment where the temperature is varying to extremes, absolute vacuum, harmful radiation, and you cannot have repair over there normally, and you need very precise systems to work with. And also it demands high strength to weight ratio materials, new mechanisms, novel energy systems. Now let us see what a launch vehicle is. A launch vehicle, you can see a PSLV, a GSLV, and GSLV Mark III. You just look at the size of these marvelous vehicles. It weighs up to 600 tons. Look at the gigantic size. In order to even construct these launch vehicles, you need so much of materials. Very simple thing to think about. Now, apart from that, there are a lot of functional systems inside. There are pumps, there are a lot of mechanisms that are operating inside. So you need several materials and chemicals to operate this. A gist of the chemical applications in GSLV, we can have a look at it here. It varies from stage to stage. You have several materials coming, starting from propellant resins, potting compounds, adhesives, flame-resistant material, and so on. Depending on the requirement of each stage, you have so many materials all over the vehicle that you have to make. And when it comes to satellite, you have battery cells for energy storage. Tremendous amount of energy has to be stored, what is available from sun. And then you have liquid propellant, oxidizers, special films, adhesive for insulation, and thermal paints, and solid film lubricant. Now, to sum up, chemical science and engineering in space missions. It starts from propellant and propulsion, polymeric products, foam products, ceramic and composites, energy systems, electronics. We can classify into these major elements. Let us look at the propulsion and propellants. We all know we have chemical propellant, we have ionic propulsion, we have nuclear propulsion. Let us focus on the chemical systems. We have solid, liquid, cryogenic. A chemical rocket is what? It employs an exothermic reaction, produces hot and high pressure gas products, and this gas, when it escapes at very high velocity, provides the thrust. It is a well-known science now. Now, how to select this propellant? It's very tricky. In the sense, you have to look at the thermodynamics and physical properties of this material, you have to look at the chemical properties, and one has to screen exotic fuel oxidizer combinations. You have to see metals, hydrazines, hydrogen, amines, hydrocarbons, and so on as the candidate propellants. And there are oxidizers starting right from oxygen, fluorine, nitric acid, then hydrogen peroxide, and so on. And one has to do very controlled combustion tests and simulations to really identify the required propellants for your propulsion system. And here comes how to identify. There is a number called ISP, which is nothing but the thrust a propellant can give per unit flow rate. You have to maximize that. How to do it? You have to design very carefully a chemical system, a molecule to perform all these aspects. For example, you can see a solid propellant binder, and you need to start with a small molecule and then polymerize it to form a very precisely designed long chain molecule to give you the required performance in flight. So this is one very important application of chemical scientists and technologists have to overcome. Now, another important element, a rubber sealing. You have explosive materials that are to be handled, materials and gases that are to be handled, high temperature and pressure conditions that are existing inside rockets and satellites, massive structures, numerous joints, wide temperature, stringent leak rate requirements, and media compatibility. These necessitate a robust sealing like O-rings and gaskets, wide size range, large numbers, high safety precautions. You know, in a conventional pressure cooker at home, what is the role of the gasket is playing in that. Everybody is aware of that. And here comes the one critical element, the rubber sealing in launch vehicle, and the Challenger disaster is a classic example of what is the role of rubber sealing in a launcher. Now, another important element we are coming to, it is ceramics. What are ceramics? We can define it as a non-metallic, inorganic solid compound that are formed by the application of heat and sometimes heat and pressure. So it may contain a metal, metalloid or a non-metallic elements, at least two of them. And they are held together by ionic bond, covalent bond or a mixed bonding. We have different types of ceramics. It could be oxides, it could be silicate, it could be nitrate, it could be carbide. Now let us take an example, silicon carbide. It is one of the most well-known material that are used in space community, and it comes from a naturally occurring material called carborundum. And the beauty of this is silicon carbide is not attacked by any acids or alkalis or molten salts even up to 800 degrees. And another beauty is that in air, silicon carbide forms a protective silicon dioxide coating at 1200 degrees, and it helps us to withstand a temperature even up to 1600 degrees. A self-created material it is. It is used in space shuttle. You can remember the Columbia disaster where the loss of a ceramic tile cost the entire mission lives of so many who were traveling in that. Now move on to polymeric adhesives and coatings. There are numerous joining and bonding that need to be done in launch vehicle and satellite. There are various requirements: structural load, environmental protection, insulation, thermal conductivity. You have to meet wide temperature range, vacuum stability has to be met, in situ pre-bonded structures have to be made. Generally, epoxy, silicone, acrylic systems are considered. It requires very careful selection, design of materials for performing these tasks. One example would be for the chemistry of adhesive. Let us consider silicon. It has got SiO-Si bond, and this is even stronger than the well-known carbon-carbon bond. And they are heat resistant to other organic polymers. Even it can withstand even more than 300 degrees. And they have got a very peculiar structure. Let us move on to that structural aspect. You can see it has got a SiO-Si bond, and in that you have on the outer side methyl groups, and this gives a very beautiful capability to this adhesive, because these methyl groups are water repellent. So an adhesive coating, a material coated with this adhesive can repel water, and this water will not seep into it, and it gives you a self protection to that. Let us move on to another important element: polymer pipes for cryogenic application. Many of you may be aware that liquid hydrogen and oxygen are handled in launch vehicles. You have to deal with temperature as low as 10 Kelvin. Which material we can think of for handling this? For example, from the tank, liquid hydrogen and oxygen need to be transferred to the engine. What pipe can withstand that temperature? There we have the solution: polyimide pipes. It is a right combination of low specific gravity, low stiffness, mechanical strength, flexibility, etc., and it meets the facile conditions, and also it is processable. So designing, material selection and development and processing really a challenge to any scientist and technologist in this area. Now, energy systems, 25 to 30 battery packs of different sizes are used in a launch vehicle. all along the vehicle from bottom to top. And multi-kilowatt power requirements are therefore in that type of satellites. Now, if you look at launcher, it is a single-use application. You need high power for various requirements. There are silver zinc battery cells, there are lithium ion battery cells, two well-known systems. When you look at satellites, it has to meet more than 10 years and they have to be rechargeable. It has to take solar energy and it has to store it whenever it is needed, it has to produce it. So you have lithium ion cells, well-known lithium ion cells which are available in almost all mobile phones that are available today. Another requirement would be round-trip requirements, long duration requirements. Shuttle, RLVs, reusable launch vehicles, manned missions, Moon, Mars, base, here these kind of requirements are coming. Here the technology is what I mentioned a little earlier, the fuel cells, which is non-rechargeable, but it has got multi-day capability and multi-kilowatt power with good scalability. It works like an engine. Now, when you look at solar system explorations, there is another power system called radioisotope thermoelectric generator, which works for decades. Another important area is electronics. One may wonder what is chemical science and technology has to do with electronics. There are multiple application-specific precise components and circuit boards in a launch vehicle and satellite. Now look at the semiconductor processing. It requires ultra-high pure materials. Impurities at PPB level and highly sensitive operations are involved. It requires very special chemical process to make this. It involves printing precisely with zero defect tolerance, micron thick printing and plating, basically electroplating, numerous chemical operations and very high parameter sensitivity. So electronic components are fully founded on chemical processing and engineering capabilities. Now, science is about observing and questioning. Science gives us the never-ending urge to find answers and solutions. Here, I was trying to take you through the major chemical science and technological applications in our daily life as well as space missions. Thank you all for listening. Thank you.